All right.
Okay, thank you everyone for coming. Tonight we're going to have a talk by Sang-woo about Morse theory.
Okay. Just before we begin, can everyone hear me all right? Is the sound level okay? Okay. So we'll start with a fundamental example that we'll be visiting on and on running. That is of the Morse. That we envision as being sitting upright in a glass tank. That is slowly being filled with water. And we're going to study how the portion of the torus that is submerged underwater changes as the water level rises and falls. And you'll see how this change in the portion underwater reflects on the topological properties of this entire torus. And that is the idea of Morse theory that we hopefully will be able to touch on briefly. Okay. To make this idea formal, let us introduce a couple of notations. I'll start with that. And imagine of this thing as a real line, and that h is a function that takes this torus, each point of the torus, to the height of this point. So envisioning this torus inside R3, and this is just taking this to the z coordinates. So h would just take this to z. And the way we think of the water level rising is just going to be the value of h, the height function. And you will let a denote the preimage, which is just a fancier way of saying this is the portion of the torus underwater when the water level is at a. Something like this, yeah, and a. Now, what we're going to do is we're going to vary a, so that corresponds to changing the water level, and you're going to see how MA looks like on the first. There are a couple of critical points that you have to note. We have this critical point, which is the only point that intersects with this plane section when the water level is at 0, and you have this critical point, and also this critical point, this critical point. These are points where the shape of the submerged portion changes dramatically as water level passes through these points. So keeping that in mind, we will examine the situation with a is 0, and a is between 0, and this point, which are going to concretely say is at 1/4. And this one at 3/4 is concretely this one at height 1. So we're going to examine a between 0 and 1/4. We're going to examine a when it's at 1/4. And 1/4, and you can see how it goes from there. Zero, MA is just a point, because that is the only point submerged underwater. When A is between 0 and 1/4, it would be dissected somewhere up here, in the shape of something like. Whereas A approaches 1/4, the gap here gets smaller and smaller, and eventually at the critical point A equals 1/4, this gap will close and you get something like this, so this converges into a single point. And as A grows beyond this critical point, what you get here is going to be that this shape grows a pair of edges. Something like this. And the critical point again. This endless, as we approach the critical point, this endless starts to get closer and closer. And at this critical point, the endless converge into a single point again. Something like this, which you should think of as a cylinder that is pitched at a single point. And over here, this thing goes a bit further, and we get a torus that is a discrete, so it's just a torus as a whole. And finally, at the critical point of A equals 1, this hole shrinks into a single point, and the hole is closed, and we retrieve the torus. So you can kind of see how, when you're dissecting this, there are a couple of critical points where the shape changes dramatically. And we want to capitalize on these dramatic changes and reconstruct the torus from these little shapes. Actually, now these shapes are already kind of difficult to analyze. They are, well, in this case, the torus is not bad. But let's think of simplifications of these shapes. Let's see what happens when we try to continuously deform these shapes into simpler shapes. So by continuously deforming, we are allowing, think of them as being made of very compressible plates. So we can compress them, but we can't let them freeze them or anything like that. It's a little weaker than homeoplasticity, but that is the equivalent relation. So in the case of a point where a is equal to 0, there's nothing to do. It's already quite simple, and a simplification. And by continuously deforming a single point. And between these two critical points, there is nothing new here, because this disk, you can imagine, is using your hands to push it down into a single disk, and everything collapses into a single point somewhere around here. And something interesting happens when we move to the next critical point. This you can't really push down into a single point as we did before, because this point, when you try to push it down, you have to allow for some self-intersections, which we don't want to do. But what you get instead is when you're trying to hold this shape in your hands and push it down along the circles into the center circle over here. You can see that you can continuously deform it into a single circle, like this. And of course, between the two critical points, the situation is completely similar. You can all push it down all the way, and it will continuously deform into this particular circle. So there's nothing new. But again, similarly, something interesting happens when you pass to the next critical point. This thing, by issues that we just described before, you can't continuously deform it into a circle, but you can continuously deform it into something similar. Imagine you're holding it down, and you're using your thumbs to press it down like this. So the shape you're going to be reaching towards is something, I don't know if I can call it. Okay. So it's two bands attached together, and there's a single page over here. Now we can deform this further. These things have a central circle. These bands. And you're going to kill this with, like pressing them further. And what we're going to get is a wedge of two circles. Now, two circles identified as a single point, which we will call a wedge of two circles. And past this critical point, nothing new happens as usual. Over here, nothing new happens. Because you can do a similar argument to continuously deform this thing into these wedge of two circles. And then the last critical point where you cap all this all, so you can treat the whole torus, which you can't really continuously deform any further. So if you were to organize this into nice little pictures, what we get is that at the first critical point, second, loss, namely the one A equal to 0, A equal to quarter, A equal to quarter, which are just this, and this respectively. We get a nice simple spaces that we are earned by analyzing the portion of the torus that measures the water. Over here is just a point. Over here it is just a circle. Over here it is a circle identified as a single point. So it's a wedge of two circles. And over here it is a single torus. Now, a crucial parallel observation to make is that we could have constructed this torus by simply looking at these diagrams. The idea is that we study this point, which is a zero-dimensional disk. We actually use the word cells for this. And then we attach a one-dimensional cell, which is just a closed interval. By identifying the two ends of this closed interval at this zero cell. So what you're going to get is a single circle. And according to this, we attach another dimensional cell. This time over here. And lastly, we attach a two-dimensional cell, which is the product of the closed interval of this cell, which is a square. Now, in the familiar way, if you have a square, you can turn it into a torus by identifying all these edges in a systematic way. So this we attach to this shape by identifying this edge, which is really a circle, to this circle, and we attach this edge over here, which is this is also a circle because in the torus it gets identified to a circle. And if you fold it in a nice way, this will sit inside the usual torus like this. Simple functions that can get out of this analysis. And that is the motivation, the idea of Morse theory that we're going to explore. It turns out that this deconstruction and reconstruction phenomena can be done on any general spaces, general nice spaces called smooth manifolds. So, having said that, before we move on, let us do a quick recap or rapid course in smooth manifolds by trying to motivate the definition of it. So, analyzing things on the torus, and in this case, we're analyzing a specific function, the height function. And ideally, we want to do some sort of calculus on it. Say, you have a function on the torus, and you want to analyze its minimum or maximum. You want to check, you have to analyze how this function changes in a certain direction. And the only way you're going to be able to do this is by trying to come up with a notion of differential calculus of this course. But that is not very easy to do, because the only notion of differential calculus that we're familiar with, at least from calculus, is the notion of differential calculus between functions between Euclidean spaces into the real line. So how do you try to piece together this definition to make amends for the functions of the torus? There is one way. Say, we want to define the derivative of the function of f on the torus n at point P. What we do is we cut out a nice little neighborhood of this point that resembles unit open ball. In this case, it would be a unit of this R2. And you want to do it continuously, and you also want to do it reversibly. So the condition we're going to now is that this function phi, which identifies this little concept, with this unit open ball is going to be continuous, and it is a projection, and its inverse, by inverse is also continuous. Such functions, continuous bijections with a continuous inverse, are called homeomorphisms. And it's a basic equivalence relation that we study in topology. So, having said that, this sits in the Euclidean space, and if we follow these arrows, it goes into the real line. We can kind of devise a notion of differential derivatives here. Namely, this point P is taken by phi to this point P. And we can kind of define the derivative of f at P by the derivative of the composition f by P. Well, this is kind of doable because this sits in the Euclidean space, and its domain sits in the Euclidean space, and its range sits in the Euclidean space too. But there are a couple of issues with this definition. Firstly, you need a guarantee that you can always find such open sets that resemble open balls in every single point of this torus in order to have a notion of global derivative. Otherwise, you will only be stuck with the notion of a local derivative only around points where you can find such a thing. So the first problem, there is no guarantee. We can find such there is also another problem. This one is a problem of well-defined. Say we have two another function that resembles the unit of a ball, and another function, phi, that identifies this as a unit of a ball. Then there are two competing notions of derivative here now. We could have defined the derivative this way, by composing a phi inverse. We could have defined it this way, by composing a phi inverse and just computing a point corresponding to p. So there's the issue of well-defined. And it is actually even worse. Before we ask whether we can compute a derivative, we must ask, is this function even differentiable at all? It's not a guarantee. So, and it can even happen that this, if you follow this line, it is differentiable, but if you follow this one, it is not differentiable, and you would have jeopardized. So, to fix this, we do not try to alter our definition of derivatives, but we try to restrict the collection of spaces that we are taking interest in. So we're going to study very specific spaces where these kind of issues do not arise. And these spaces are precisely as smooth manifolds, which I'm going to define usually. But hopefully this is the only concrete definition I'll have to make. I'm just showing it by so a sufficiently nice space and is called a smooth manifold of dimension n. For every point there exists an open set U containing P that resembles unit of the ball Pn, which is unit of the ball in the Euclidean space of dimension n. And by resemble, we really mean there's a homeomorphism between them. And two, for each choice of identifications that is identification morphisms from U to N and sine from V to Vn, such that these two open sets overlap at P. Then the transition functions, y compose the sine inverse, and that's from some open set in the unit of the ball into some open set in the unit of the ball is differential. So what we're really doing here is we are giving restrictions, we're giving constraints onto these identification maps by requiring outright that this map, where we trace the arrows like this, is supposed to be differentiable. In fact, when you say differentiable, you always use smooth, meaning infinitely differentiable. So we require that this arrow, which are maps between Euclidean spaces, are smooth. And you'll see how that this first edition either solve this first problem, because by assumption you can always find such open sets. And two, this question is not fully addressed by this criterion, but it is partially addressed in the sense that the problem of well-definedness of smoothness is at least well-defined. But you'll notice that the well-definedness of derivative is still not well-defined, because different choices could still give you different numerical values of this derivative. And this is an issue that is a little tricky to solve, and for our purposes we won't need it, so we're going to talk in recursive. But you still have to notice that since this function is smooth, we can take this function's derivative, and you can switch the orders of these two, because this is for each condition. So you can argue the same for psi composed with phi inverse, and yet this is true. And if you compose these two maps, you notice that these two are inverses to each other. So what this means is, this map is a smooth map, whose inverse is smooth. And by the chain rule, we now know that this function, the derivative of this function, which is n by n matrix, must be invertible. So what this guarantee tells us about this definition of derivative is that if this derivative is 0 for some choice of phi, then it must be 0 for all choices of psi. So what is well defined is not exactly the definition, not exactly the numerical value of the derivative, but vanishment of the derivative. Meaning that, well, the numerical value of this thing might not be well defined. If one of them vanishes, then it vanishes for all. So we can say that the derivative is 0, and that would be a well-defined notion. In Fullerton calculus, when we have analyze function, where the derivatives vanish, it is justifiable to introduce the following definition too. Okay. Continuing from that, then f, the smooth function is smooth method. Meaning you pull back, if you compose with all these little identifications, the map between Euclidean spaces are all smooth. So a smooth map is said to have a critical point. If the derivative of f at p vanishes. So from our discussion earlier, it just means you choose some identification, check if this derivative is 0. And this relates to our story about the torus, because the critical points that we mentioned earlier, where the shape of the subject portion of the torus changes dramatically, are precisely the critical points of the height functions between the torus and the real line. So what I'm saying is that this function turns out to be smooth, and if you try to find little identification around these critical points, you can verify that the derivatives that we could use vanishes at these precise points. And these are all the critical points. And before we move on further into the story of Morse theory, let us draw from a familiar example from calculus, where he did something very similar. So first we will restrict to single variables. So starting with the modified function from R to R. And it is differential. And you're doing critical point analysis of it. Meaning you want to look at minimum, you want to look at maximum. And the first thing you would probably do is you take the derivative. Find points. The derivative of p is equal to 0. And this is not precisely in this critical points of f in the sense we just defined before. And you notice how, if you draw the graph, you notice how we can extract the information about the graph, which is a curve sitting in R2. By looking at the second derivatives of f at a critical point p, there are a couple of cases. If the second derivative at a critical point is positive, then we know that from calculus we know that this thing p must be a local minimum. So this tells us that the graph of f must locally look like a cup. And if the second derivative is negative, then it must be a local maximum. And the graph of f would locally look like a cap. And in the degenerate case, where the second derivative 0. The test is inconclusive, and we can extract no geometric information about the graph amount sitting in our square. And this relates to the story of automoting the torus like this. So we imagine this graph sitting in a two-dimensional water tank. And we also find the quartz medium. Then the height function of this graph is just f, in the sense that you take x and move on to this function, xy. And the height function takes this to y. Since this point sits on the graph, this must be the image of f at x. So, critical points of the height function. The critical points of the height function is the same thing as the critical point analysis that we did in high school calculus. And this is one manifestation of the idea that we just explored in torus. And something more interesting happens when we move on to higher dimensions. Say, a function defined in Euclidean space of dimension n. To concrete, just let us stick to dimension 2. So this time f is a function within our square. That is smooth. And say p is a critical point. And this time around, the derivative of f and p is no longer a function. It's a matrix. It's the Jacobian matrix. So we have to be a little careful about what we mean by critical point. We call it the Jacobian in this case, we just define the partial derivatives. Evaluated in phi. So when we say it's a critical point, we mean that these two edges will vanish. They all go to 0. And we can do a similar critical point analysis as that. And the second derivative is positive. Although ideally we want to do something like this. But we will quickly run into the problem that this does not really work. It has to be very nicely. Because we don't really have the immediate notion of second derivative that comes directly, that we can compare nicely between positive, negative, and 0. In fact, the second derivative here is going to be a larger matrix. Which is called the Hessian. And this is just the matrix with all the entries of second derivatives. So here's the very specific value. This is the second derivative here. Negative definite or minor. Well, of course, we'll have to assume that this thing is invertible on right. And of relevance to us is the following lesser known result from linear algebra, which is called Sylvester's law of inertia. If there exists invertible matrix P such that B equals the transpose of P multiplied by the left to A, and that P multiplied by the right. You see the similarity with the equivalent, more familiar equivalent relation, which is similarity, but this thing is referring to the inverse. The philosopher doesn't really consider congruence, but this is just transpose. So the significance of this equivalent relation is that congruent real symmetric matrices give rise to equivalent symmetric bilinear forms in the sense that they are equivalent of their phase change. recall that if you have a real symmetric matrix, you can induce a real symmetric bilinear form, symmetric bilinear form, by defining x by the x transpose multiplied by a on the left and multiplied by 1 on the right. And this will give you a 1-by-1 matrix, which is reinterpreted in real scalar. Okay, so keeping that in mind, and so this law of inertia tells us that every real symmetric matrix is congruent to a matrix, to a diagonal matrix with entries 1, 0, or minus. And we will make a definition that if this, if A is a real symmetric matrix, we define the signature of A to be the triple and plus and minus and 0. And plus is just the number of ones that happens in the diagonal that occurs in this diagonal matrix. And then minus is just the number of minus ones that occur in this diagonal matrix, and 0 is of course the number of zeros. And we will make a couple more sideline definitions. If n0 is equal to 0, so that this diagonal matrix is invertible, then we say that A is non-degenerate. And if A is non-degenerate, we call n minus the index of A, for reasons that will be apparently known. Okay, so this is law of inertia says that this is an if-and-only-if condition. If two real symmetric matrices give rise to the same diagonal matrix after congruence, and of course they are congruent because reflexivity. Okay. So
is the signature of A related to the signs of the eigenvalues of A?
Oh yes, it is. You can actually formulate this result in a completely different way. You can just ignore the diagonalization and say n plus is the number of positive eigenvalues, n minus negative and so on. Okay, so going back to the Hessian matrix, while it doesn't make sense to do this critical point analysis as in single variables, it can do something similar. So, when we are restricting to the two-dimensional case, we have 3 cases, or 4 cases. But there's the Hessian is non-degenerate, and the Hessian is degenerate. In this case, the test is inconclusive. This is the degenerate case we have explored before in a single variable case, and we do not have any geometric information. Now, if it's non-degenerate, there are 3 cases. Depending on the signature, we will discuss this as 0 points. And by dimensional argument, we see that the only possible combinations of signatures are 2, 0, 1, 1, and 0, 2. As mentioned before, this would just mean that this one means that the matrix over there is positive definite, this is negative definite, and this one would be neither. Okay, so let us analyze this one first. We want to analyze the graph of it, which should be the surface in our place. And by the same argument that we did behind functions, the critical points of f and the critical point analysis will transfer into the critical point analysis of the height function of this surface. Projecting it here. Okay. So when the signature is 2, 0, it means that both, it means that in every single direction, the derivative of f is, the derivative of f would be positive. So by the critical point analysis that we did on the single variable case, then this thing looks like a local minimum in every single direction. And I guess it makes sense to say that the graph of F would look locally like a cup around the critical point of signature 2, in the sense that the Hessian has signature 2 completed. And over here, you do the same thing. In every direction, the critical, the derivative, the single variable derivative is looks like a local maximum. So the graph over here looks like a cat. And a new phenomenon occurs when you're dealing with mixed signatures. In in some directions, the function would be coming downwards, but in some directions, the curve will be coming upwards. So what you're going to get is something we can reasonably call a seven. I think I'm going to make next one. Did you get it? So in some directions, the curve looks like a local maximum, but in some directions, the curve looks like a local minimum. And all these examples showcase that we can analyze the geometric, topological properties, geometric properties of the surface by looking at critical points of the height function. So with these little experiments, then you can transfer all this knowledge into the smooth manifold case. Then the cinematic critical point analysis will give you information about the smooth manifold. And this indeed happens, and is the content of the celebrated Morse method. So that and the compact, meaning if you put this inside the Euclidean space, it's closed and bounded. Smooth manifold. And that from M to R is a smooth function. Non-degenerates, but with no degenerates critical points. As before, we now introduce a notation that A is a pre-image. So in the analogy of the torus, this would be the same thing as the semi-nice portion of the torus, and the water level is an IA. And this Morse lambda tells us that the critical point analysis gives us information about how these MA look like. So, case 1, well, that A and B become numbers. If this pre-image contains no critical points, then A and B continuously deforms into MA. This was, recall what we did with the torus. So if you have something like this, you saw how this J can be continuously deformed into a single circle. So what this first criteria, first result tells us is that if there is no critical point between water levels A and water levels B, then MB and MA are not fundamentally different in the sense that they give rise to the same simple part of the manifold. And 2, if P is sense that it's a little weaker than continuously deforming. So to make sense of this result, let us go back to the example of the torus and see how this result is consistent with what we had done in the torus.
What's that index of the SCM?
Oh, that would be the, remember that this thing had a signet thing. Plus, minus, and 0. The index is the number of negative components. So this was why we figured out and this would be only important part that would be lines of Morse theory. Okay, so let's go back to the torus. And let's see how this is consistent. We have the first critical point, a equals 0, which is just a point. That's nothing new here. And you have a critical point 1 quarter, 3/4, and 1. Now between 0 and 1/4, and A, as we mentioned before, looks like this, which can be continuously deformed into a single point. And this is consistent with the first part of Morse method that says that if F index AE contains no critical points, then the two things F, A, and D are continuously deformable into each other. So this is consistent with Morse method, and something new happens when we reach 1/4. This closes, and you get this shape. And to apply Morse method, we can't look at the interval 0 and 1/4 because the interval we're working over here is the open interval. So we have to move a little bit beyond 1/4. So we'll have to make the quarter level somewhere here. Let's say this is 1/4 plus epsilon for small epsilon. So what this tells us is that MA over 1/4 plus epsilon, the Morse method tells us that that thing has, it looks like this, with a cell, a dimension, the index of this critical point attached. And if you compute out everything here, you realize that the index of this thing is 0, the index of this critical point is 1, the index of this critical point is 1, and the index of this critical point is 2. In the sense that if you compute the critical points of the height function to R, and do the business that we've done, you can compute these things out. So Morse method now will tell us that this thing will look like this thing with the one-dimensional cell attached, which is just a closed interval. Consistent with the findings because if you explicitly compute out what this thing looks like, it looks something like this. And you can see how this thing is done from attaching one cell like this to this. In the sense that you deform this thing down and you retrieve this shape. And beyond this part, between these two critical points, nothing new is added. We keep this shape. And this is consistent with Morse method, telling us that nothing new is added between these two critical points. And finally, at the next critical point at 3/4, there's something that looks like this, which can be seen as something that looks like this, as you can deform one to each other, attaching a one cell to this shape. In a sense, you can pull apart this part while keeping this identification set that you get this shape. Conversely, if you kind of squish around this part and compress it to a single point, you retrieve this shape. And in that sense, they look alike. And finally, beyond this critical point, Morse theory tells us that there will be nothing new added, and which is indeed the case. Because between the critical points 3/4 and 1, the shape takes the shape of the torus as a whole. And this and this doesn't look that much different in this isolated definitions. And finally, the last critical point, the closing of this gap. And by closing of this gap, you should think of this as we're attaching a cap into this epsilon to form M1. With this can is really a two-dimensional disk. This has flip this thing out against that disk. And this is consistent with the index of this critical point. Morse theorem tells that M1 would look like something that has M1 minus epsilon with a two-dimensional disk attached. And it is indeed the case. So I hope this example illustrated how kind of illustrated how Morse theory is consistent with the very fundamental example we observed. And immediately, there's one application I just found in this lemma that I would like to say. This tells us that this process is general in the sense that Morse lemma gives us a recipe constructing or decomposing the manifold into simple spaces. So let's take a function that has no critical points. And you chop out the critical points. Then you analyze how the portion of the water, that is Pi minus epsilon and Pi plus epsilon vary. Morse lemma tells that these things vary when attachment of cell of dimension k. Where k is the index of the critical point Pi. So the upshot is that you can deconstruct the smooth manifold into simple pieces, which are these, which we can further deconstruct into simple pieces where it continuously form. And then we can reconstruct by retracing this process. So this thing would be done by attaching some cell, and then you attach another cell, and you keep attaching cells. And this is what we did in the very first example, where we started out with a 0 cell. We attach one cell, we attach another one cell, and we attach a 2 cell to form toys. And spaces where you can do this, meaning you can start out with some toys, you attach some cells, you attach some 2 cells, and so we'll have a special name, and they're called CW complexes. So what Morse lemma immediately tells us is that every smooth manifold admits the structure of a CW complex naturally. And this has some implications in topology because it simplifies a lot of things. In the sense that CW complexes are much simpler to work in the eyes of algebraic topology. And there is an application. Called Reeb's lemma. If N is a compact smooth manifold, function with no degenerate points, and in fact, if it admits precisely 2 critical points, then that is a sphere. So this thing has got a simple proof, a scheduled proof. Okay, so that is a contact manifold. So F being a continuous function of the contact manifold, it must have a maximum and a minimum. The maximum and minimum, they are critical points. Okay, so the assumption that this F has only 2 critical points forces that these maximum and minimum are the only critical points of F. And in general, you can compute out that minima as index 0, maximum as index full index in the sense that as index equals to a negative F. And the construction part of Morse lemma tell us that you can reconstruct N by starting out with the cell, that corresponds to this linear mesh, which must be zero cell because it's an index 0. And then you attach a cell of dimension m. In this case, this is just going to be a disk, a ball of dimension m. And there's really only one way of attaching this cell to a single point along the boundaries, which is you crush every single point of the boundary into a single point. But if you identify every single point on a Euclidean ball, what you get is a sphere. So most of them immediately tells us that M must at least look like a sphere in the sense that it is homotopy equivalent. So I think this is a cool application, a nice application of this most level business. And let me just check the time. Okay. So let me just end with a little more advanced application of Morse theory that I found really interesting. For those of you who are familiar with topological topology, you might have heard of recurrent knowledge. So if you had very nice idea of proof of this one. So, say you have a smooth function m on R, no degenerate critical points. The Morse theory gives you a cellular chain complex in the sense that it gives you a CW complex structure on M, and it lets you form a chain complex out of these cells. And at each dimension, you get a cell corresponding to the index of f at a certain critical point. Now you can see that you flip f. Now you can see the minus of f to r. And when you flip this, you notice that the critical points have the index reversed. So if P is a critical point of f with the index k, then over here, P becomes a critical point with minus cells with index minus n minus k. This gives you, and minus that being a smooth function with no non-degenerate critical points, gives you a cellular chain, but in this case, one chain complex. And the identification between critical point cells given by the index of the critical points here, and the cells given by the index of the critical points here, give you a nice isomorphism that you can kind of check to translate to this Ricardo duality. Yeah, I think that's a good time to end the talk.
Is there any similar thing with the Morse theorem with Leib to, let's say, R2 with higher dimensions?
There are some generalizations, like self theory, but I don't think that is the correct generalization, in the sense that if you have a function in R2, you can just look at the components, and you get two functions, right?
Right.
So you can just compare it to Morse theory. But that is a generalization. So I think that's pretty much it.
Will it be like a definition?
You would have to analyze the testing of the individual functions that come from the components.
Would they have like percentage?
No.
Take the
If it's smooth, yeah.
abstract it, but the function that what is getting filled, there is some height, it has some speciality to it. Okay, you cannot use just any arbitrary function, I guess. So how is that? Is that captured somewhere in this definition? In behavior keyword?
The speciality of the height function is that there are no non-degenerate critical points. So if you take any function with no non-degenerate critical points, it turns out that the choice, as you said, that the choice of the height function is a little special. Because say you let the corners flat like this, and you consider the height function, and the critical points are no longer non-degenerate, mainly because every point on this bridge and every point on the bottom bridge are going to be critical points. And they are a little much more difficult to analyze.
That's a great question. I didn't expect this to yeah.
Yeah, that's rare for Math Club talks. You did us a great favor.
First time this time.
Oh, I actually had some more things prepared.
Oh, yes.
I mean, if you... I
I
think
mean, you want to add it?
Oh, no, it's okay.
I think it's very nice that we get to go home. I'm very excited to go home.